Good afternoon, everyone. Hope you are doing good today. I decided to start a new lecture series on VLSI subject. VLSI, as it stands out, very large scale integration. It is the design process by which we combine billions of transistors and make a working integrated circuit. Or you see in day-to-day life, you see your cell phones, television, computers, you have all those electronic gadgets, fancy gadgets, what you use. There is a tiny chip, and on that tiny chip it is assembled, or I should say it is manufactured by assembling billions of transistors on a single chip. In this lecture, I'm going to be discussing about different design abstractions. Since we are talking about chip design, VLSI, semiconductors, it's very important that we should know about different design levels or abstraction levels. That's where the famous Y-chart comes in picture. It is a very simple chart. It just gives a pictorial representation of different design levels in VLSI process, the complexity at that level, how we transfer the same description from one data abstraction to another abstraction. So let's start. Mainly, we say that there are three dimensions: behavioral, structural, and geometrical. 3-dimension, it's a number 3 is a very powerful number. It comes in our day-to-day life again and again, again and again. You see, 3-dimension, we live in a three-dimensional world. Of course, Einstein proposed that there is a 4th dimension in time, and physicists, scientists believe on and all that, but we are living on Earth, and let's talk about only, let's continue discussions up to 3 dimensions only. So in the VLSI design world, we talk about behavioral dimension, structural dimension, and geometrical dimension. The behavioral dimension, what we have here, we define or the behavior of the system, or what your chip is gonna do. In the structural dimension, we define that what are the different components this chip has, how those are connected, how much memory, what are the processing units, whatnot, those kind of things. At geometrical level, we define that how the different components are gonna be laid out. So we, design floor plans, we plan out, it's like a building structure. If a builder decides, okay, I buy this land, and how I'm gonna organize this land, how I'm gonna develop this land, how many buildings I would have on this land, where the swimming pool would be, or all those sort of amenities would be. So that sort of thing is there at the geometry level. Now let's go a little deeper in geometrical area. So we define physical partitions. What does it mean? It is very similar to, like, as I was saying, the builder example. Builder buys the land, decides, okay, I'm gonna build 3 buildings or 4 buildings. They share common facilities like parking, like swimming pool, like a common outside area, barbecue area, rooftop patio area, and so on. Now let's go further, level up. Within one building, how many units you will have, what portion of the building will have the shopping units, what portion of the building you have residential units. So you kind of make a clusters within one building. Now you made the all clusters. Now at the macro or floor plan level here, what you do, you take out just one, let's say one floor, and then you design how many units I can make at that floor. Good. Make a macros, you can call it a macro or floor plan. And then within one unit, how the things are going to arrange. Within one unit, how many bedroom you're going to have, where the kitchen would be, where the washroom would be, all those sorts of things within one unit. So one unit becomes one cell, and you do all floor plan for that particular cell. And then once you have done within one unit particular, floor plan for one specific unit, you have, okay, at this place I'm gonna have my bedroom, in this corner I'm gonna have my washroom, in this corner I'm gonna have my kitchen. Now within that area where the things gonna fit, like where you're gonna have shower within your corner of your washroom, but where you're gonna have the stove within your kitchen area, you draw small polygons to depict the pictorial representation. So that covers up all basically the physical dimension or geometrical dimension of the design. Now let's talk about structural dimension. What do I mean by structural dimension here? That you define the data transaction or the between the bigger units like CPU, processing unit, memory, buses, those sort of things you define there. Now let's go one level down. At this level, you define the subsystems. Okay, subsystems means that okay, I have this small subsystem, say print subsystem, within a full system on a chip. So the print subsystem gonna have its own internal bus, its own little internal control unit, its own registers and whatnot. So it's a small subsystem within one big block. Within that subsystem is self-sustainable subsystem. You may have arithmetic logic unit, registers, and whatnot, different components you can arrange. And that within, if you go one more level down, you can create logic gates or flip-flops. And then if you open it out, if you tear logic gate apart, what will you see? You will see small transistors. Good. So transistors becomes the basic unit under the structural dimension, which corresponds to polygon. Actually, you make a transistor at a circuit level, and then you draw polygons to make a floor plan, or how in physical reality is gonna look like, where the polysilicon layers would be, where my metal layer would be for one particular transistor. Good. Now let's talk about behavioral dimension. Behavioral level, say we define the system. Okay, this mobile phone chip is gonna, what is gonna do? It's gonna do all sorts of things. It's gonna control my voice, it's gonna control my apps. It's kind of a full chip which is doing everything, starting from receiving your call, Wi-Fi connectivity, all sorts of functions. So you define at the system level, like an architect is defining the whole thing, how this system gonna work. And then, once you have this whole system, then you're going to come up with certain algorithms, how I'm going to process that. Okay, you have the hardware, you have things, but if it's not going to, it doesn't know how the hardware going to work. So you write certain algorithms, okay, A equal to B plus C, whatnot. You try to depict the system level functionality in terms of, you convert in terms of algorithms. And then those algorithms, in terms of which are in terms of pseudocode, you convert in a register transfer level description. What does it mean by register transfer level description? That you write the operations which fetch data in and out from the registers. Basically, you try to come up here at this level, the design description which tries to, so one part is the memory element, and where the values are stored for temporary operations, and then the gates, which are logic gates, which are trying to perform the logical operations which your algorithm defines. Okay, so we convert it at register transfer level description. And then finally, we have register level, transfer level. If we tear that apart, then we move on to the basic logic level, 0 and 1 level. Good. And then we finally, in the very end, we say, okay, this is the transfer function. It's the very basic element in the behavior dimension, transfer function. Okay. So you see the complexity in semiconductor design process. Now it was a smart thing. Let's try to find a relationship between these three dimensions and different points along these dimensions. So if you see closely, we can draw circles like this circle, bigger circle, that becomes one level, which has three dimensions but at one level. Another circle, second level, different dimensions. Third level, different dimensions, and so on. See how simple it was. Now, interesting thing here. Those of you who want to go become a system architect, you should try to focus on getting more expertise in the behavioral dimension. Or those who are good with the structure or with the things which you like to see, you'd like to draw polygons, you like to do floor plan, those sort of things, you should develop your expertise in geometry or physical dimension. And those who are not concerned how the system is going to work, but those who are concerned how the system is implemented, those should focus onto the structural domain expertise. I hope this lecture would help you to guide yourself into different possible design areas, so that at the end of the degree you don't get confused where I should be doing, what I should be doing, what makes me happy, what not. So think about it, take your time, think about it on all different design abstractions, different dimensions. That may help you. Again, those who haven't subscribed LEPROFESSEUR channel, please subscribe to LEPROFESSEUR channel. This will help you to get new videos as soon as I post them. If you need private lessons or tuitions, you may contact me at hr@leprofesseur.org. And thank you once again who have joined this channel, who have subscribed this channel, and thank you for your comments. Hope you have a very good day. Thank you.